Let us determine the support moments for the given loading conditions. Here a continuous beam having supports at A, B, C and two spans 4 meter and 6 meter A, B, B, C. On AB it is subjected to UDL 6 kilonewton per meter and on BC 10 kilonewton per meter. For the given loading conditions we have to find out the support moments. We know very well at A and C the moments are zero as it is simply supported ends, and it is required to find the support moment at B. According to moment distribution method, we have to consider the individual spans as individual fixed end beams. Suppose consider span AB as individual fixed end beam. A is fixed, B is fixed, and for BC, B is fixed, C is fixed. Now for the individual fixed end beams subjected to UDL, how to find the fixed end moments? Formula we have seen already. That is AB at A, the moment will act anticlockwise minus WL square by 12. At B, MBA plus WL square by 12. Similarly, for span BC, fixed, MBC anticlockwise minus WL square by 12. And then MCB clockwise, so plus WL square by 12. Okay, so W is nothing but the corresponding UDL on the corresponding spans and length with respect to the corresponding spans, span 1, span 2. Substitute the UDL and length, you will get the respective fixed end moment value or fixed moments, whatever it is. Okay. So enter these values minus 8 plus 8 in this tabular column, minus 8 plus 8. This is for span AB and this was span BC, minus 30 plus 30. Now we need to find the distribution factor in order to distribute the unbalanced moment in the moment table. Now B is the joint which is common to span BA and BC. So BA, BC are the two members. B is the joint. BA, A is simply support. So 3 by 4 I by L. You have to use the relative stiffness formula. BC, C is simply supports. Again, you have to use the formula 3 by 4 I by L. So here I remains same because we are taking a uniform section, uniform cross section of the beam. So I1 is equal to I2 is equal to I. L1 is 4 meter and L2 is 6 meter. Substitute here, get the relative stiffness for the member BA and BC. Then total relative stiffness is nothing but sum of these two. 3I by 16 plus I by 8 is equal to 5I by 16. Distribution factor is nothing but 3I by 16 divided by the total relative stiffness 5I by 16. You will get this. Then I by 8 divided by 5I by 16. You will get 2 by 5. So this is for BA. This is for BC. For BA 3 by 5. For BC 2 by 5. So enter the values. This is nothing but fixed moment values. Now we know that at A and C the moments are 0, but we have assumed it as a fixed end beam and we have obtained some value. So we have to make that moment to be 0 at A and C as it is simply supported end. So we have to release at A and C. Release at A and C means we have to carry over that unbalanced moment. So minus, so plus 30, I should make it 0. So put minus 30. So now it is balanced. So this is balancing the unbalanced moment should be carried over to the intermediate support. So minus 30, carryover factor is 0.5 or 1 by 2. So minus 30 into 1 by 2 will get minus 15 plus 8 multiplied by carryover factor 1 by 2 you will get plus 4. So now you just draw a line here. You add these values. You will get 0 plus 12 minus 45 and plus 30. These are called as the initial moments. Okay, initial moments. Now we have to distribute the unbalanced moment. How to distribute the unbalanced moment? This plus 12 minus 45, add these two, you will get minus value, some value. So some value will get minus some 33, for example. If you get minus 33 means this is the unbalanced moment. I want to balance it, so I should consider plus 33. Okay, so if I get minus 33 means I should consider plus 33 in order to balance the unbalanced moment. So plus 33 multiplied by 3 by 5, you will get plus 19.8. Then plus 33 to 2 by 5, you get this answer. This is nothing but DF, distribution factor. Then you draw a line, add this value, add this, add this, add this. Then the support moment at the intermediate support B is nothing but plus 31.8 kilonewton meter. This is the final moment answer. So this is the answer for the given loading condition. Next problem, we are having three spans A, B, B, C, C, D. So we have to consider two spans, right? A, B, B, C, where B is the common joint, B, A, B, C. B, C, C, D, C is the common joint, C, B, C, D, C, B, C, D. Then B, A is simply support, so 3 by 4 I by L. B, C, see, B, C. Beyond C, I am having support. Let the support be simply support or a fixed end. The formula should be I by L. Then CB, beyond B we are having support, so I by L. CD, D is the simply support, you don't have any other support beyond D, so it should be 3 by 4 I by L. So I1 is equal to I2 is equal to I3, L1 is 6 meter, L2 is 5 meter, L3 is 4 meter. Substitute here, you get the relative stiffness. Total relative is sum of these two stiffness. Sum of these two stiffness. Distribution factor, this I by 8 divided by 13 I by 40, you will get 5 by 13. I by 5 divided by 13 I by 40, you will get 8 by 13. I by 5 divided by 31 I by 80, you will get this. Then 3I by 16 divided by 31 I by 80, you will get 15 by 31. Then by considering the individual spans as individual fixed end beams, AB fixed end beam and BC again one another fixed end beam and CD is another fixed end beam. By considering individual spans as individual fixed end beam, we have to find the fixed end moments. So this is the formula. Fixed end beam subject to an eccentric pointer formula is minus WAB square by L square. Why minus AB anti-clockwise? MBA clockwise plus. Formula is WBA square by L square. Substitute, so this is nothing but A is nothing but 2 meter, B is nothing but 4 meter. BC, A is 2 meter, B is 3 meter, like that. Okay, so minus WAB square by L square for MBC anti-clockwise negative, MCB clockwise plus WBA square by L square. So find out all the values. And for CD, MCD anti-clockwise minus and MDC is clockwise plus. So minus WL square by 12 plus WL square by 12. So substitute corresponding W, that is UDL, and the corresponding length to get the fixed end moment values. Enter all these moment values on the distribution factor in the table. Okay, this is MEAB, MBA, MBC, MCB, MCD, MDC. This is the common joint B, BA, BC distribution factors. For C, CB, CD, this is the distribution factor. Now we have entered the fixed moment values and distribution factor. At A and D it is simply support. So release at A and D, add with the same value opposite sign. Add with the same value opposite sign. At A and D make it 0. Then you carry over this moment, unbalanced moment, to the intermediate support. Plus 8 multiplied by 1 by 2. Minus 4 multiplied by 1 by 2. This is the carryover factor. Now draw the line. Sum up the things. Sum up the things. Sum up the things. Sum up. Sum up. We call this as initial moments. Now, so these are the unbalanced moments. This one should be distributed between or among the intermediate supports. So 8 minus 5.76, you'll get some value with negative. Okay, you'll get some value with negative. So that value should take it as a opposite value. That is the same value with opposite sign you should take. And that value must be multiplied by 5 by 13, you'll get this. And that value multiplied by 8 by 13, you'll get this. Similarly here, 3.84 minus 6, you'll get some negative value. Take the same value with opposite sign, multiply by 16 by 31, multiply by 15 by 30, 15 by 31, you'll get distribution factor as this one. And draw the value, sorry, draw the line here. Carry over this unbalanced moment. That is this value multiplied by 1 by 2 and this value multiplied by 1 by 2. Carry over factor. Again distribute it plus 0.558. You have to consider minus 0.558. That is nothing but we are balancing the unbalanced moment. That means we are making the moment to be 0. So here I'm having 0.558 plus is the unbalanced moment. I want to balance it. So same magnitude with opposite sign. So I should consider minus 0.558 multiplied by 5 by 13. Here minus 0.558 multiplied by 8 by 13. Here also I should consider plus 0.689 multiplied by 16 by 31. Here multiply by 15 by 31. This is the distribution factor you get here. So now carryover factor 0.356 into 1 by 2 minus 0.343 into 1 by 2. You get this as the carryover factor. Then plus 0.18. I want to balance it, so I should consider minus 0.18 multiplied by 5 by 13. Minus 0.18 multiplied by 8 by 13. Here minus 0.17 I should consider plus 0.17 multiplied by 16 by 31 multiplied by 15 by 31 distribution factor. Again you carry over plus 0.08 into 1 by 2 minus 0.11 into 1 by 2 carry over factor. Again you distribute it plus 0.04, you get plus 0.04, consider minus 0.04 into 5 by 13. Here minus 0.04 multiplied by 8 by 13. Here minus 0.05, so consider plus 0.05 into 16 by 31. Here into 15 by 31 distribution factor. Now you can see here, this is a kind of iteration process. We are trying to converge our results. If you get same value on either side, okay, you get plus 0.02 plus 0.02, and here also the same value on the other side. You have to stop our iteration process. Now you add from here, okay, from here to here you add it, you will get this value. And here also you add it, get this. This is the final moment value. This is the final moment value for the given problem. So MB is equal to say plus 6.83 clockwise for BA. For BC, MB is nothing but minus 6.83 kilonewton meter, which is anti-clockwise. Similarly, for MC is 4.5 plus for span CB plus for span CD. It is minus anti-clockwise, so minus 4.5 kilonewton meter. So in this problem, you have got three spans of same length throughout the beam. Same value of UDL is subjected to 1.5 kilonewton per meter. Okay, AB, BC, B is the joint, BA, BC is the member, BC, CD, C is the joint, CB, CD are the members you can see here. BA, A is simply support, so 3 by 4 I by L. BC is beyond C we are having a support, so I by L. So CB beyond B we are having support, so I by L. CD, D is a simplest support, beyond D we don't have any supports, any beam, so 3 by 4 I by L. Substitute here, I1 is equal to I2 is equal to I3, L1 is 5, L2 is 5, L3 also 5. Substitute, you get the total relative stiffness to be, you add these two, you will get 7I by 20, you add these two, you will get 7I by 20 again, because same length. Okay, moment of inertia also same, so you'll get the same here. And distribution factor, this 3I by 20 divided by 7I by 20, you'll get 3 by 7, and I by 5 divided by 7I by 20, you'll get 4 by 7. And here for CB, I by 5 divided by 7I by 20, you'll get 4 by 7. And for CD, 3I by 20 divided by 7I by 20, you'll get 3 by 7. Now, by considering the individual spans as individual fixed end beams, we have to find the fixed end moments value, fixed end moments value. Okay, everywhere it is UDL, same length. The formula for a fixed end beam with UDL is WL square by 12. Okay, anti-clockwise minus, clockwise is plus. So same length, same UDL, so you'll get the same magnitude here. So anti-clockwise minus 3.125 kilonewton meter, clockwise plus 3.125 kilonewton meter. So enter all these fixed end moment values and the distribution factor in a tabular column. You can find here 3 by 7, 4 by 7. Okay, A, B, C, D, right? BA, BC, then CB, CD. Enter the fixed moments values. A and D are simply supports. Let us release at A and D. Carry over this moment. Multiply by 1 by 2. Multiply by 1 by 2. Draw a line, add it. Add the values. Okay, now here 4.688 minus 3.125 will get positive value. Consider same value with negative sign. Multiply by 3 by 7, enter here. Multiply by 4 by 7, enter here. Here 3.125 minus 4.688, you will get negative value. Consider same value with opposite sign. Multiply by 4 by 7, multiply by 3 by 7. Okay, this is nothing but the distribution factor. Then carry over again between the intermediate supports 0.89 into 1 by 2 minus 0.89 into 1 by 2. You get this value, carry over factor. Now plus 0.45 is the unbalanced moment. I want to balance it. You consider minus 0.45 multiplied by 3 by 7. You will get this minus 0.19. and minus 0.5 multiplied by 4 by 7, you'll get this. And here I should consider plus 0.45 multiplied by 4 by 7, you will get this, and multiply by 3 by 7, you will get this. This is a distribution factor. Again, carry over 0.26 into 1 by 2 and minus 0.26 into 1 by 2. This is a carryover factor. Now plus 0.13 is the unbalanced moment. Consider minus 0.13 multiplied by 3 by 7 multiplied by 4 by 7. And here you consider plus 0.13 multiplied by 4 by 7 multiplied by 3 by 7. Distribution factor. Now you could see here same values here, same value more or less. Now you add the values. So this is the distributed, this is the final moment, plus 3.76 kilonewton meter, and here also plus 3.76, because same length, same util, that's why we get the same answer here. And this is the final moment answer for the given beam with the given loading conditions. Thank you.